All right, so today we're going to talk about the one lecture on operating systems. Yeah, this is going to be a sprint, but it's all we got time for. So I'm going to talk about virtual machines, containers, microservices, and unikernels. I'm assuming you've got most of the basic OS stuff from 3.33 down, so this is a riff off of that. Assuming you know what a regular operating system does. But before I start with this, I am going to assign homework number 3, which is to take that recipe app that you just built and then implement the a SQLite 3 model that supports insertion and viewing of recipes. Yes?
Just to clarify, when it says reviews,
it means recipes. Dang it. Yes. Okay, and just because I'm OCD and a little bit anal here, where is this one? I swear if I don't do this now, it'll never get done. I'll be doing this for many lectures. Okay, so create an HW3 directory for your application. Yeah, you're not going to be using the dictionary model. You're going to be creating your own model that implements that abstract sort of the model class from the capital M model that you've defined. And it just has to implement the insert. So now you can insert on one route. And I want you to create an additional route for creating the recipes. And you probably have already done this if you use an MVP style pattern. But there should be separate pages, one for inserting new recipes and then one for viewing all the recipes that have been submitted. All right, so the backend is a SQLite 3 database. And if you go back to the database lecture, you saw in the guest book, there was a SQLite 3 model. And the SQL that you need to insert, it's all there. So it's just a matter of adapting it to your recipe site. And just to get you repetitions using SQLite 3. Okay, so that's homework number 3. Are there any questions about homework number 3? Okay. So let's start with virtual machines and containers. I'm going to take you back in time. Probably this predates before most of you have been born. To this computer. This was one of the first computers I ever had. This is an Apple IIc, and I think I got this in 1982 or 83-ish. And this was back when floppy disks were actually floppy. They weren't these things that you see here. In fact, I don't even think any of these have floppy drives anymore. Yeah, there are no floppy disks anywhere. Okay, so what the hell? Why am I teaching you about Apple IIcs? I promise you, before you go and you tell my brother, give me my money back for this course. Just humor me to the end of this, and there's a point to talking about the Apple IIc. But this Apple IIc, this brings back very fond memories. So the Apple II and my other computer, the TRS-80, these were systems where you had a computer that had a single memory address space with real memory. And you had a single CPU that was never shared, right? It could only run one thing and one thing at a time, and that was it. And the way these computers worked was you typically had an operating system disk, a floppy disk, and you would turn the computer on with that disk, and it would load the operating system from that disk into real memory. And then you would eject the disk, and then you would have a separate program disk. And then the operating system would load that program from the program disk and overwrite itself. It was basically setting itself up to run another program. But when you took that program disk and executed it, it wiped out the operating system that was there. It allowed you to run your program, but the operating system wasn't there anymore. So when you wanted to run another program, you had to turn the computer off, stick the operating system disk in there, turn it back on, and then you could run the second program. So you're continually rebooting your system because this was a real memory system with a real CPU that could only run one thing at a time. So that's where at least my computing history starts. And then we came, the next class of computers that we got was this thing. So this is an original Mac. So what do you think this added to the Mac? Why am I showing you this? We certainly weren't doing the same thing as we were doing before. What do you think might have been different with the original Mac? Yes? A GUI. Okay, a GUI, a real GUI with a mouse. Yes. Yeah, windowing. So that's definitely true. Yes. Virtualization, kind of, sort of. Maybe later Macs. But this is like really the first Mac. So it's still a real memory system. But it allowed you to have multiple processes sharing that real memory. So it wasn't completely, it didn't virtualize the entire memory system, but what it did was it allowed you to have the operating system, and the operating system was given a certain part of real memory. And then if there was enough memory left over, you could load a program into the other parts of memory and then go back and forth between the operating system and that program. And in fact, if there was enough memory, you could actually have two programs, and then you could task switch between the two programs. So I have a picture of the calculator. If I had maybe a word processor, which I couldn't at the time, I didn't have enough memory for a word processor, but if I had some other toy app, like a task list program, I could run both the calculator and the task list program, and then click back and forth between the two of them, and the programs were running there, resident in memory, and I could run one or the other back and forth without having to reboot the system as I did with the Apple II, or the Apple IIc. Okay, so this enabled you to switch between processes and programs that are running on that system, but it's still a single shared real memory address space, meaning that there's the addresses that you would use in your application went from 0 to the capacity of real memory that you had on the system, and that was it. You got one of those addresses, and if you had that address, no other application could have that address. Okay, so the issue with the original Mac was that it did not provide any isolation between the apps. And not only between the apps and the operating system, there was no memory protection and no memory isolation. And so anytime you had poorly written code, which you always have, anytime you had memory errors in one application, it would just spray all over memory and you would bring down everything else. So this is something that I was really familiar with running a Mac. Anytime an application error happened, you had to restart the entire operating system every single time. And hopefully that application that caused this crash would eventually get fixed, and you'd be able to install a version of it that wouldn't do this. Okay? So this brings us to these systems, the Intel i386, Windows NT, and from long ago, the IBM 370. So what do you think these systems brought to the equation in terms of a computing system? What is the key thing? Yep. Memory virtualization. So that is what first appeared on Intel with the i386, and then integrated with an operating system with Windows NT, and then IBM had it in the 60s. Actually in the early 70s. So this had been rocking and rolling on mainframes the entire time. So the IBM 370, 1972, and then eventually Windows NT 20 years later, they figured out that this was a good idea, so then Windows and x86 started adopting virtual memory. And so the idea here is that you have a bunch of applications, they each get a virtual memory address space that's all of their own. It appears that they own all of memory, but there's a trick that the operating system and the memory controller, the hardware memory controller, are playing on the application to basically multiplex these virtual memory address spaces onto the real hardware that's delivering the location. Okay, so that's what the operating system and hardware are coordinating to provide you, this abstraction of a uniform memory address space where every application believes that it owns all of memory. And so the way this works is that the operating system implements a namespace for the memory subsystem. And the namespace concept is really important because that is basically what runs virtualization. Anytime you think about virtualization, think of a namespace, and that namespace is actually determining what version of memory you're going to look at. Okay? And so in this case, the namespace created by the process ID, in conjunction with the virtual memory address that that process is accessing, will then map you into the real memory address that the hardware has stored that particular piece of data. So namespaces for memory are basically resident in all the operating systems that support virtual memory. And so you could have two processes have a virtual memory address 0, and they're stored differently in real memory because their process ID is different. And the operating system and the hardware are using that process ID to map that virtual memory 0 into two different locations underneath. Okay? So the other thing that this allowed is that each process now can believe that it owns the entire CPU. So if you combine the virtual memory address space with appropriately time-sliced CPUs, so if you take the CPU and you share it across all the different processes, then that basically allows you to give the process an abstraction that it's basically a virtual computer. Okay? Okay, so this is the virtual computer-ish abstraction, and it's not actually a full virtual computer, and we'll talk about the limitations that this particular approach has in a bit. Okay, so here's a picture. I'm going to start putting things up in a graph, or in a figure. So we started out with the machine on the left, which it's a single process machine. It's got real CPU, real memory, and a real operating system that's running. Then we went to this multi-process shared memory, and again, it's real CPU, real memory, and a real operating system, but they're all sharing that address space with each other. Finally, we just talked about multi-process virtual memory. It's both a virtual CPU because you're time slicing the CPU across multiple processes, and it's virtual memory with the namespace that you are giving to the underlying real memory system. But the operating system there is real, meaning that there's only one instance of the code that runs all of that. Okay. So the question becomes is what resources are not virtualized in the operating system? The operating system is virtualizing basically just the CPU and memory. What else might you want to virtualize in an operating system that might not be? Throw something out there. System calls, right? So maybe I need a different set of system call, well, if I'm accessing resources through a system call interface, maybe I need separate ones for separate operating, or separate versions of programs running. So there's one. Anything else? Can you share the same port between processes running on a single operating system? Can I put two web servers up? I can't. The processes have their own version of the virtual memory address space, but they don't have their own version of the network ports. The web server port, for example. Only one process can own the web server port. So it's not quite full virtualization. You're not virtualizing everything. You're only virtualizing memory and this CPU time slice when it comes to operating systems like these. Okay, so the processes are all sharing the file system, the networking ports, any of the users and groups on your Linux system. Those are all shared between all of the applications running on that system. So it's not really a true virtual computer because you have all of this, you can see all of the other resources that the other applications are using on that system. Okay. Moreover, if you have a security problem on one of the processes and it gets into the file system and it gets into the underlying operating system, you have a full break on all the other processes that are resident there. So there's a security issue there. And this is what motivates virtual machines, which you're probably really familiar with. with this class. So a virtual machine virtualizes the hardware in order to allow multiple operating systems to run on that piece of hardware. This is a namespace for the hardware. So now when the hardware gets the name of the VM that a certain resource request is for, it can figure out which version of the VM it's processing that request for. So you're virtualizing the underlying hardware and allowing multiple operating systems to share that single piece of hardware. Okay? So the virtual machine that you're multiplexing on top of the hardware contains the entire operating system. It's completely not shared between virtual machines that are running on the same system. Okay? So all of the operating system and all of the application state is put into a single machine, and then this virtualization layer right here is the thing that will give you a namespace on top of the actual hardware that's running underneath. So, for example, if you run a Linux VM if you run a Linux VM on this Windows machine, the file system is virtualized. The disk is virtualized into a single blob that's on the Windows machine. That VDI is like you virtualized the disk itself in that VM, and that's the idea of VMs. Okay. So the virtualization or hypervisor layer is basically decoupling the operating system from the hardware that it's running on. Before, these things were tightly coupled, but now you have a level of indirection. You can apply a namespace to the hardware to allow you to put multiple virtual machines transparently on top of a single piece of hardware. And that's the benefit of doing a VM. So this does enforce machine isolation and resource isolation between virtual machines. Each virtual machine sees its own CPU, memory, network components as well, its own operating system, and then the storage is isolated between VMs. Now typically this isolation is quite strong, but this is only in theory. So in practice, this last summer with the Spectre vulnerability, as long as you are resident on the same physical hardware, there are side channels that actually allow you to do cross-VM stuff. And that was this was the devastating part of Spectre, is that now if you're running on the cloud, an adversary only has to get onto that same shared machine as you to be able to get all your secrets. And this is the reason why over the last couple of months, Google Cloud has these sole tenant virtual machines. Like if your sensitive application, so none of mine are sensitive, but if you have a sensitive application, you would want to run that on a sole tenant VM just to make sure that the thing is isolated from anything else that's running on it. But theoretically, I mean, the ideal is that these VMs are isolated from each other if the hardware doesn't give you away. Okay. One of the things to note is that the namespace has gotten hardware support to make it extremely efficient, and this is why you would enable the VTX and the AMD features in your processor, because it's basically hardware acceleration for making this thing switching between VMs fast. Okay, so virtual machines are an ancient idea. That IBM 370 actually had it in 1972, and the reason why it started to take hold in the 90s is that finally, in 1999, x86 got its first hypervisor from VMware. And so it took basically 20 odd years for the virtualization approach to get from IBM all the way to Intel x86. And as soon as that happened in 1999, this is where you started to get cloud deployments where you could actually multiplex multiple virtual machines on a single piece of hardware. Okay, so why would you virtualize? Why was this revolutionary? Well, the reason is before virtualization, you would have physical servers running your mail server, your database server, and your web server. And typically, those servers would only take a very small percentage of the resources on that machine. Only when they were getting requests were they busy. If not, they were completely idle. And so you can get like if you had these three machines running on as virtual machines, you could get the isolation that you wanted across these three different servers without taking the performance or the cost of having 3 physical machines. So if they were all, this is statistical multiplexing, right? Like this is exactly what packet switch networks did versus circuit switch. Rather than have dedicated mail server, a dedicated database server, a dedicated web server, I can multiplex those as virtual machines on a single piece of hardware, and then you statistically multiplex their usage across that single piece of hardware is effectively what's going on. Okay. And by doing so, consolidation is great, but you have to worry about security. And one of the things with consolidating it with VMs is that because they are theoretically isolated from each other, a security problem in the mail server won't spill over to be a problem with the database server or the web server. And the idea of doing this is now the idea behind these operating systems where every single application is run in a virtual machine. On Windows, there's this thing called Bromium, where the Windows version of that is every single app runs in its own VM. And the reason why they're doing that is to get the isolation in between apps running on the same system. So these are modern approaches that are doing this. Okay. There are multiple ways of implementing virtualization of virtual machines. The 2 types that we're going to talk about are the Type 2 and the Type 1. The Type 2 hypervisor is what you're currently running on your desktops. And so the idea here is that you have a host operating system. So in this case, on these, you have a Windows 10 operating system as a host. And then you install VirtualBox. And VirtualBox will run this virtualization layer on the host that will allow you to run a guest operating system. And in this case, this is the Ubuntu operating system. And anytime the Ubuntu operating system as a guest has calls that need to interact with the actual hardware, it will trap into the virtualization layer, and the virtualization layer will call into the host operating system and then into the x86 hardware itself. Okay? And so all of those privileged calls made by the guest VMs will eventually get forwarded to the host operating system. One of the issues with this is that the actual guest operating system that you run has to be hardware compatible. So in this case, they all have to be x86 based operating systems for you to run that virtual machine on top of the host operating system, or this particular machine, which is also x86. So some examples of Type 2 hypervisors are VMware Player, Virtual PC, VirtualBox, which I had you install, and then on a Mac it's Parallels. The other kind of hypervisor that you're going to use is the Type 1 or bare metal hypervisor. The approach removes the host operating system. Instead, you run the hypervisor directly on the hardware, which is what this virtualization layer is. And then all of your VMs run on top of this Type 1 hypervisor that's running directly on bare metal. This is what all the data centers are running. So all of the Google Cloud stuff on Compute Engine, they're running the Type 1 hypervisor, which is based on KVM for Google Cloud. And they're using that to run all of the different VMs that you're instantiating on Google Cloud. I think Amazon runs Zen. And then Microsoft runs their Hyper-V as a type, actually. Yes. So KVM is Google, Zen is AWS, and then Hyper-V is used by Azure. So these are all Type 1 hypervisors that are meant for data centers. Basically, hypervisors to run virtual machines, arbitrary virtual machines. Okay. So this is our figure next. So on the bottom right, we've added virtual machines where you virtualize the hardware, but the operating system is the real operating system. There's one version of the operating system, and then there's the hardware is the thing that the operating system is decoupling over. Okay. Are there any questions about this picture? Yeah.
What's the difference between a Type 1 hypervisor and an operating system?
Typically, an operating system is not virtualizing another operating system. So the hypervisor's goal is to be the interface between a guest operating system and through the host operating system to get to the hardware. Yeah.
It seems like they do the same function. Just run applications, the interface between applications with hardware.
Similar, but the nice thing about the hypervisor is that you can have multiple You're having multiple operating systems multiplex on that, whereas just a regular operating system is just multiplexing processes through the system call interface. This is more at the hardware interface level. So it's just the layer in which you are splitting the thing up, where in a regular operating system, the process layer and the system call interface is where you're multiplexing, and in this case, it's the underlying hardware is where you're doing the isolation. Yeah.
Does the operating system going to share the internet port for the host operating system?
You can set it up not to. So in the way I had you set up your VMs, I had it in NAT mode, where it would actually go through the host in order to get the networking, and then it would basically set the host up as a NAT router to do the networking back and forth, and that made it hard. It makes it hard for you to run servers on your VM. If you ran it in bridged mode, then that would virtualize the actual network interface card. And so when we talk about virtualizing hardware, that's what you want. I can have my VM have a completely separate IP address and have its own networking stack that talks directly to the hardware when I do a VM. If I had just regular two processes in a regular operating system, they are definitely sharing the same IP address, sharing the same ports, but because I virtualized the network interface card, the hardware itself, then a port 80 request for one VM will go to one spot and another VM would go to another, and it would have multiple IP addresses. I showed the example of virtualizing the network interface, so that's basically what the hypervisor layer is doing. It's virtualizing the network interface card in order to give it the abstraction of separate hardware for separate VMs. That's correct. Any other questions? Okay. So this is where we are now. So there are some issues with virtual machines. One of them is startup time. So bringing the virtual machine up and down requires an entire operating system boot process. So on Compute Engine, you say, I want to instantiate this VM, and then you have to wait for like 2 minutes, 2 or 3 minutes. This is not appropriate if you need to bring machines up and down very quickly, right? You don't want to have this startup cost. The other problem with VMs are the size. If you have, for example, the mail server, the database server, and the web server, if they're all running Linux, you have just copied an entire Linux distribution 3 different times, and you're running 3 different versions of Linux on top of that single piece of hardware. So this is replicating a whole bunch of operating system code and a whole bunch of library code on a VM that could potentially be shared. Ideally, that code would be shared. And this also requires, because each version of each virtual machine is also taking up the real memory address space for their own version of the Linux kernel, this means that you have to have a whole bunch of RAM, a whole bunch of memory, in order to host multiple virtual machines on that single piece of hardware. And so for me, I have like a 16 gig of RAM machine in my office, just because I run multiple virtual machines, and I have to use large amounts of memory for each one of them in order to get reasonable performance. Okay. So what you would really want is isolation between virtual machines without replicating the whole stack. So that's what is ideal. It's also not quite portable. So virtual machines running on one cloud provider don't work directly on other cloud providers. So for example, Google has KVM. The disk image of a KVM virtual machine isn't going to work directly on Amazon. You can't just say, copy this image over to Amazon and have it work. They're not directly portable at the hypervisor layer. And so you can actually Google moving EC2 instances to Google Compute Engine, and you can see the pages of stuff you have to do. You have to serialize the disk to a block device. You have to import it on the other side. This makes it really difficult to switch from AWS to Google Cloud if you're stuck on VMs. If all your stuff is done with VMs, you're not going to be able to migrate it very easily. So this motivates containers. And the idea of containers is to virtualize the operating system. So what does that mean? So far, we have the traditional operating system that virtualizes just the CPU and the memory to give you processes. And then it leaves the file system and the networking ports shared, right? You're all sharing the same file system. You're all sharing the same TCP ports. It's all still visible to each other that one process is using certain things that the other process might want. On the other end, you have virtual machines that virtualize all of hardware. Now, this allows you to run multiple types of guest operating systems on that single piece of hardware, but then now you're going to replicate the entire machine. The operating system, the applications, everything is replicated. The approach for containers is to virtualize the operating system, where the container only provides the application and any of the application libraries, and then that is all run in user space, and then the operating system itself is not replicated. Instead, it's shared amongst these containers that are running, but each container sees its own virtual operating system. They each get their version of a file system. They each get their version of the network communication ports, and they also get virtual CPU and virtual memory as before. So that is where containers are coming from. So how does this work? So the first container-enabled operating system, Linux rolled this in 2008, so it's been about 10 years. And the idea here is to provide namespaces inside of the operating system. So every single resource and every single system call has this notion of a namespace where you are running that request on behalf of a specific container. And that's how you can get the namespaces for different containers to share the same operating system, but make it appear that they have separate operating systems. And it's just like virtual memory with a PID being the differentiator. In this case, there's something else that's used as a differentiator, but that's the idea, okay? So it's similar to PIDs, but it's virtualizing everything else that you want virtualized. The file system, the network resources, the block devices, all of that gets replicated. Okay, and then the container layer, within the operating system, between containers, that's where you enforce isolation. That's where you do the resource allocation, the scheduling between containers, all of that stuff. One of the problems, or one of the issues with going to this approach is that now only operating system compatible containers can run on top of that operating system. It's not like virtual machines where you can have both a Windows VM and a Linux VM running on the virtualized hardware. If you're virtualizing the operating system and it's a Linux operating system, you can only run versions of Linux on top of that operating system. So most containers, so when you run containers, it'll typically run on a like a Linux container on top of a Linux host is basically the canonical setup that we're going to have in this class. Okay. This is what it looks like. So the virtual machine, you have the application libraries, and then the entire guest operating system multiplexed on this hypervisor that's providing you a namespace into the hardware. In the container world, you have the application and the binaries and the libraries, and then the namespace is implemented in the operating system itself. So all of this operating system stuff is shared between multiple containers, whereas in the VM approach, the guest operating system is replicated across the hardware. So that's functionally what's going on with containers. Are there questions about that? Okay, so the way this is implemented is with C groups or control groups, and this is the thing that's providing you the namespace. So when you do your Docker labs, you'll see that every container's got a name. It's got a name that's very memorable for you to use. That gets mapped into a specific C group in the underlying Linux kernel to provide the isolation between the containers. It's basically, you can think of this as the name that's being used to separate the containers from each other inside the operating system. And so you use this feature to do the isolation of the applications and the applications within the operating system. So this allows you to have separate process trees and process identifiers. So when you do a PS in if you have two containers running on the same host, if you do a PS on one, you'll have the process ID 1 as the init process. If you do it on the other container, you'll also have a process ID of 1. And the thing is the namespace is being implemented in the host to give you two different versions of the same PID. And if they were just processes on the same operating system, they would all see the same process tree. So in this case, if you do a PS on that container, you only get that container's processes. Okay. The same thing with the networking system and the sockets. You have a separate user ID space, right? Like you can have two different users, like foo and bar on two different containers, and when you look in the etc password on one, you won't see each other, right? Whereas if you're two processes on the same operating system, all you have to do is take a look at etc password and see which users are on there, and then you can have multiple applications seeing each other on that shared operating system. In this case, they're completely isolated because the namespace isolation in the operating system. Okay. The benefit of this is that you have very minimal replication costs in space and in memory for all of that shared operating system code. In the VMs, if you had 3 Linux VMs, you're copying all of that code across each VM. Here, they're sharing all of the Linux code. So the kernel is only in memory once. Okay. So this is providing people with similar, it's not identical, but it's similar isolation and protection, but much lower overhead. They're also faster starting, right? Like creating a namespace in an creating a new name within an operating system is much faster than booting an entire virtual machine up from scratch. So you can bring up containers left and right, and it'll be within a second. You say, Docker start that image, it's there running immediately. You don't have to wait for an operating system boot. And then the memory footprint is much smaller. So it turns out you can do 4 to 6 times more containers on a single piece of hardware than you can running VMs. Okay. It's much more portable, right? Because the compatibility layer is not the hardware layer. It's actually the operating system layer, and the operating system layer is pretty much standard, right? Like the Linux interface, right? So that's where you can put containers. You can move containers from provider to provider, from on-premises to cloud, left and right. Like they just work because the portability layer, it's done at a layer that's good for portability. And so it's repeatable. So it's both portable and repeatable. You can run the same container anywhere, and they'll be run similarly. And so this solves the works on my machine problem that you, like this is a bugaboo in industry. It's like, it works on my machine. I don't know why it works on yours. And then and that's the end of it. All these containers will run the same way for wherever they're deployed, typically. And so this solves my problem in courses for repeatable labs. Because then I don't have to worry about, oh, you're running Windows and you're running a Mac. I can't figure out the difference between how that thing runs. That stuff goes away with containers. Okay. You'll see that for continuous integration and continuous deployment, this is really a boon on that. Because as you are going from dev to production, it used to be that process wasn't seamless. Like getting a developer's environment, because the developer is installing stuff left, right, and center to get their app to work. And then to get that environment over to a production server is quite manual. And so if you have sort of set up your production environment, you can commit that to a Docker container and then upload it, and then the production people can just pull it. They can just do a Docker pull, and they'll get that image. And we'll talk about the mechanics of doing this in the lab. Okay. And then you get some security compared to the traditional operating system, but you lose on security compared to VMs. So VMs are typically the best way to get isolation. But in terms of security, if you had your mail server, your database server, and your web server all running on the same server, at least if they were run on separate containers, then a break in one wouldn't result in a break in the other, unless you actually subverted the Docker layer, the container layer itself. So that's typically a security benefit of containers. And so one of the things that's happening is that because you get this isolation and you get some security benefits, a lot of the traditional monolithic web apps are being split up into this microservice architecture. So the idea of a microservice architecture is to take the different subparts of your app and turn them into isolated containers that talk to each other. And so this microservice architecture is where software development is now sort of shifting over to. And so before, on the left, is the traditional approach where you have your entire application with a front end, a back end, and some application code all running on the same machine, as you see here. And then as soon as you have your full application running on a single machine, then to scale that up, you would replicate that machine across multiple hardware servers. And so the way this would scale up is to clone the app. So with Docker and with containers, people are moving more towards these microservices deployments, where the application is segregated to the subpieces, and then each development team that is in charge of a particular subpiece can then work on that piece in isolation from the other dev teams. And then when they're deployed, they can be deployed as separate microservices that just interoperate. And so then you can basically make changes in your one microservice and not have to coordinate its deployment across all of the other services running on that app. Okay? So for example, the one that Home Depot, I listened to a podcast on how Home Depot went to microservices, and they were like, yeah, we had this shopping cart thing, and then we had the store locator thing, store locator part of the site, and then we had the suggestion service, which is doing some machine learning thing, and we're like, we couldn't run that all monolithically. Like, we couldn't have all those dev teams coordinate to deploy those pieces of individual functionality on our production website. And it ended up being logistical nightmare in terms of just coordinating all the dev teams. And so what they did, they took the shopping cart feature and they made that a microservice. And they have a team that's all they do. They build the shopping cart stuff. And they have the coupon service, completely separate on another microservice. And then that's what gets deployed. And that's how you can incrementally deploy your different microservice without coordinating across all of the other parts of your application. Okay. That's a funny cartoon about containers on XKCD, which I'll skip. An aside is Google is all in on containers. This is their corporate strategy to dominate the cloud. And so it is used everywhere in Google. So all of their main services, search, mail, maps, the data processing stuff. So MapReduce is the way they used to do everything with MapReduce. The Google file system, so Google Drive, all of these things are run as containers. And this allows Google, from an infrastructure standpoint, to get away with a lot less hardware, right? If you're not running a virtual machine for each one of these sub-applications, and you can multiplex multiple containers on them instead, you save a whole bunch more money, or infrastructure costs. And so the statistic is billions of containers every week are launched on Google Cloud just for their production sites. And so when you launch a Google Mail session, what that actually does is it launches a container on the Google infrastructure that's custom to you to handle your mail requests on the server side. That's basically, and the way containers are done, it starts up very quickly, so you don't have to wait for a virtual machine to come up for you to access your mailbox. It's just done with a Docker container, and if you mess up your container, they've got isolation, right? Like if you're trying to, interact with your Google Mail in a way that compromises Google to try and get to someone else's mailbox, well, that's done via a container that's basically meant to be isolated. So they have that user isolation on the back end that's implemented using containers, which is very powerful. Okay, so I listened to a podcast, and this person's like, we run a very minimal number of virtual machines. Most of the virtual machines they run are people doing compute engine instances from the front, right? That's like a large percent of their the large percentage of their VMs are basically compute engine instances where people actually intentionally are trying to get a VM. Okay, so the reason why they're all in on containers is because AWS has a complete head start with VMs. So the EC2, which is their infrastructure as a service, that thing is basically almost a monopoly when it comes to virtual machine technology. And so they saw that and they did not want to go after that space. Instead, what their approach is to make everything, to move everyone to portable containers and then become the best container runner on the planet. Like, because they're making a bet that the infrastructure that they've built for their data centers that are hosting their production services, that gives them the value add, like their infrastructure gives them the value add for companies to want to run their apps on Google as well. And so rather than compete on VMs, they're going to try and shift the whole operating paradigm of the cloud to containers. And then because they're the best container runner on the planet, that's how they're going to get all the business from AWS. That's their strategy, at least. I don't know if it's actually going to work. But to do this, though, they saw that this was what they needed to do, or this was what they wanted to do. And so this is why they're making all of their container stuff open source. Because the kinds of things, the kinds of tooling that you need to shift an entire ecosystem over to a new operating paradigm requires a lot of software tools. And so they were the main contributors of the C group stuff. So all those mods from into the Linux kernel for containers and C groups, a lot of that came from Google. The other piece that they're working on to eventually orchestrate containers into microservices deployments, that stuff, which we'll see later on, the coordination software, the orchestration software, that's all open sourced and originally contributed by Google in order for them to have this foothold in sort of the mind space of people deploying servers. Okay. The note I have here is LMCTFI. This was let me contain that for you. This was the original implementation of containers within Google. So Google had this proprietary LMCTFY, and then they were managing all the software around this. And then they were like, well, I don't want a full dev team on this. And so this is where they tried to shift all of the stuff that was in their container thing into Docker. And now they're shifting all their stuff away from their homegrown solution to use the open container standard. So that's where it merged in 2013. Okay. So we talked about containers and we talked about virtual machines. Once you start using these things in the cloud, you'll find that it's hard to manage collections of these things. It's easy in a class to bring up a VM here, to bring a container up here and bring it down. But on a production site, you've got whole collections of virtual machines and containers that you have to bring up and down. You have to patch all at once. And so you could do this manually, and so there are tools for doing this, like the Docker tool, which is part of your lab. There's the Vagrant tool, which is an equivalent for virtual machines. And so you can manually go there and manage those containers and machines. But what we've seen lately is a lot of automation. And so the next step of this is rather than do this thing manually by hand, maybe I can do some automation with scripts. And so things like, if you've heard of these things, Puppet, which is a local company, Chef, and Ansible, these are ways for you to scale the management costs on multiple containers and virtual machines using a centralized sort of command and control model. The last part is complete orchestration of your backend, where all of it's automated, and this is what Kubernetes is. And this is that Google project that got open sourced for basically managing collections of containers. It's similar to the cloud deployment manager that you had in the CDN lab? You used cloud deployment. You used one of these deployment managers to launch a whole bunch of instances. That was to launch VMs. So Kubernetes is the container version of cloud deployment manager. So these two things are basically automation approaches to manage large collections of resources. And we'll talk about Kubernetes in a couple weeks in this class. Okay, so that was a long-winded way to fill in the thing on the right. So you have containers, which are actually virtualizing the operating system there. Are there any questions about containers before we do the next thing? Yeah.
Is there a place where we can read about Google stuff?
A history of containers. I don't have a resource. Yeah. Yeah. Well, when I come across some things, I'll send it on the channel. But yeah, this is cobbled together from. I listen to Google Cloud has a podcast, so a lot of my stuff comes from Google Cloud. But the Google Cloud specific stuff comes from that podcast. If you're interested, there are some archives. Actually, yeah, there is a podcast I can point you to. There's a podcast, Eric Brewer. He's the guy who started Kubernetes. So all of this stuff about Google's strategy with containers and why containers really improve the operating costs. If you Google Cloud podcast, Eric Brewer, that's the one to listen to. Eric Brewer is amazing. He's actually come across we'll be doing Cloud Spanner later on in this quarter. That's actually an Eric Brewer idea that got operationalized as a product. But yeah, that podcast is amazing. In fact, I'll try and remember to post that after class. Yep. Any other questions about this? Okay. So there are some container issues. It does sort of address the size problem. So the virtual machine is around 10 gigs of disk space. The containers are around 500 megabytes, right? You do save a whole bunch of file system space by not having to replicate the entire operating system, but still, it's about a half a gig. And the problem is that when you go to a container, a microservice architecture, the container is usually there to run one thing, right? And a very restricted sort of execution environment. And so a single process running on a container might not need the entire operating system. In fact, one of the first things that you'll see when you build your own container is what base layer are you using? And so here are two lines that say, you know what, I am going to use as my base layer the stock Ubuntu 18.04 base image. And so if you have a container that all it does is print hello world, it's a Python Flask app that prints hello world, you are stuck with 500 megabytes of code that you don't need, right? Well, maybe you need some of it, but I can guarantee you don't need all 500 megabytes of it, right? You don't need the CD-ROM driver. You don't need the floppy disk. You don't need any of that stuff. You don't need bin.ls. You don't need all of these things that come with base Ubuntu. You don't need. And so the idea the problem with containers is that they also have some inefficiencies. So you want to make sure that your container uses as small of a runtime as possible. And so the goal is to shrink the size of your container, and this will be part of your next homework, is to build a container that is as tiny as possible. And I'm going to give a prize to the 3 tiniest containers that get built in this class as a preview. But the idea is to reduce the footprint of your container as much as possible. Get rid of all of the libraries that you don't need, all of the programs that you don't need. To find a minimal base layer that your application will run on. So for example, rather than the full Ubuntu 18.04, maybe you can use a base layer. There's a mini Ubuntu base layer. There's an Alpine Linux base layer, which is what you'll be playing with in your lab. On Windows, they have these Windows Nano images, which are base layers for Windows apps that don't need the full Windows operating system underneath. Yeah.
Are you allowed to choose your own disk script?
You are. Yeah, I'll get to that. I'll get to the homework maybe at the end. Well, I don't want to give you 2 homeworks at the same time. Well, I'll describe the homework, but it's not assigned until next week. But it's a really simple homework if you've finished the homework number 3. But even if you do that, if you look at the Linux kernel and the number of system calls that it implements, it's getting close to 400 system calls. And I can guarantee you that Python Flask app that just prints hello world doesn't need all 400. So you have all of this bloat of code in your container that you might not need. Okay, so your goal is to reduce the container bloat. Do you need the USB subsystem on your container? Do you need bin.ls? Do you need the file system? Do you need the graphics subsystem on your Linux to do the Python Flask hello world? No, it's no, 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 and no. So why do I have that in there? And this motivates unikernels. So a unikernel is a single process program that's compiled to run directly on the virtual hardware. And it's typically right on top of the hypervisor. And it's a custom process that doesn't need the full-featured operating system. In fact, what you have done with this process is that you have looked at everything that this process needs in the operating system, and you've included that, and you've gotten rid of everything else. Okay? And because it's a single process, you don't need to run separate address spaces. It's a single address space because you don't need to protect it against anything else. The hypervisor layer is giving you the protection between hardware instances, and then you're running just the software you need to do your Python Flask server, right? It's figuring out all the exact code in the operating system, in the libraries, and in the app that you need to run your app. Okay, so that's what a unikernel is. So the other thing with unikernels is that it's a special packaging that makes sure that the only thing that can run is your app and nothing else, because they don't want any other code on there, because that would be bloatful. That's even a word. So the thing with unikernels, because it's only running a single program, it runs in privileged mode, right? You can actually run at ring 0 for that machine because there's only a single process. There's no context switching, there's no scheduler, there's no userland code, there's no virtual memory. You can get rid of all of that, right? And then just make the hypervisor the protection boundary for your applications. Okay, so this allows you, though, to run a whole bunch of different unikernels multiplexed on top of a single hypervisor. This gives you the benefit of the VMs, where the VMs can run Windows and Ubuntu and you name the operating system, because it's multiplexed over the hypervisor. And so this is the idea of unikernels. So here is an animation that I like. I took this from Adam Wick's slides. So here is your application, and here are all the libraries and operating system features that it depends upon, and they're not even labeled. So there's this full software stack. You know, at the top is your Python Flask Hello World, and then everything else underneath is the full Ubuntu 18.04 software stack. The idea of a unikernel is to find all the parts of code that this application needs, identify all those parts, and then bring them all in to a single address space, and then get the application to run on top of all those pieces that it relies upon. So you're taking all those pieces, and you're pulling it all into a single address space, and that's your unikernel right there. So this gives you much lower operating costs and a much smaller attack surface, because now the only thing that thing can do is run your app, right? It can't run Nmap. It can't run bin shell even. Like that thing, unless your app actually needs bin shell, it actually relies on bin shell, it can't even run that, right? So this gives you tiny attack surface, much faster response, or much lower operating costs. Okay, so this is what it looks like. So on the left, full application stack running on a virtual machine on top of a hypervisor. Here's the container approach, where you have the application and the runtime libraries on the host operating system. Here you've compiled the bits and pieces that you need out of the application, the runtime, and the host OS, and then that runs directly on the hypervisor. So that's what a unikernel is. Okay. Okay, so Galwa is a company, it's a local company here. They have built something called CyberChaff, and the idea of CyberChaff is to bring up a whole bunch of Potemkin. So if you know what a Potemkin village is, this is from Russia, I guess. In order to deter invaders, the Potemkin village is a bunch of props that look like real houses that are basically like, you know, cardboard cutouts. And so the idea of CyberChaff is to create a whole bunch of Potemkin network services And to make it look like, from an adversary, that there's a whole bunch of network services running there, when there's only a single machine with tens of thousands of unikernels pretending to be network services on their back-end infrastructure. And in order to get thousands of machines running on a single piece of hardware, you can't use VMs, you can't use containers, because containers even are 100 megabytes or so. And so the idea of doing a unikernel is to get the network protocol stuff that you need to pretend, just the bits that you need to pretend to be a server, you have those bits in a unikernel, and then you can deploy thousands of unikernels on a single machine. And that's what that's the beauty of a unikernel. Okay. So in this case, a CyberChaff node is only 16 to 32 megabytes. And this is a Haskell. This is basically a Haskell application that does this. Okay. So you get this functionality, and then that thing is pretty secure, right? Like, because there's if the only code that's there is to run the CyberChaff node, then you don't have an operating system, you don't have a shell, you don't have binaries to worry about. It's all restricted to just that node. Okay, so Docker just acquired unikernel systems, and so this is something that's basically brand new. So whether or not unikernels are actually going to get deployed, there's a lot of work to be done, but this is on the radar. But this allows me to finish the picture. And so all the way on the bottom left is this single process virtual machine, or what they call unikernels, where you have virtual hardware, but then you have the real operating system as a library. And it's a single process system that has a real operating system. And I want to show this picture. This is laid out the way it is because this is a full-on cycle. It took us 30 years to go from a single process machine all the way back to a single process machine. So this is why I put that up there, because this is ironic, right? Like, this is basically the Apple II model, but built on top of a hypervisor. So that is your crash course on virtual machines and operating systems and containers. Are there questions before I talk about Docker? Okay. So what you'll be using, so since a lot of you have experience with virtual machines and operating systems, what you're likely not to have experience with is Docker, which is the container system that's de facto standard for containers. So Docker made containers easy. So this is why it took over the world, took over the container world. And it's become a de facto standard for basically implementing application and operating system environments for you to then deploy software for. Okay. So to introduce Docker, I need to go through some terminology. The first is a container image. A container image is a static file that contains all of the libraries that you need for your container and the dependencies. This is like a program binary. This is like binls. That's the container image. That is basically the operating system or container image on disk is effectively what this is. The container is a live instance of that image running on your system. So this is more like a process in Linux, where it's an actual running container. So the figure is here, where you have your container images stored on disk. And then when you launch a container from a container image, then in the kernel, you have created a container, which is a living sort of process on that running system that is an instantiation of that image. Okay. And so the key benefit here is that it really does standardize the runtime environment for both developers and then the operation team. So typically, a workflow could be where the dev team does a bunch of building, creates their containers, and then pushes up container images. So typically in a cloud deployment, like on Google Cloud, they have their own Docker Hub, sort of basically a container repository that's private to a project. And then the dev team would push up a container image that has their operating environment for their app. And then the cloud, the operation teams can basically instantiate those on the production infrastructure. In fact, it's often the case that you have both the dev team and the IT sort of operational team share a project, and then they'll go back and forth between subnets where you have a dev subnet that's on Google Cloud and then a production one that's on Google Cloud, and they'll share the project space in terms of images. Okay, so the pieces of the Docker system, the first thing is the Docker engine. This is the runtime system that's going to manage the namespaces for you. So it does all the naming, and it does the multiplexing of your containers onto the underlying host operating system. This is the thing that handles building containers, uploading containers, downloading containers, collecting them up in the file system. You can create, destroy, start, stop. So everything is run through the Docker engine facility. Then there's also the registry service. So Docker Hub, which is I had you create an account on. This is the GitHub-like repository for container images. So this allows you to share container images across different machines and different cloud deployments, in fact. And so this is just cloud-based storage and distribution for any of the container images that you create. The registry, you can make this public or private, your Docker Hub account. For this class, I want you to make it public, because in order for the TA to grade your containers, she has to be able to pull all your images. And rather than having to deal with sharing Docker Hub stuff, I just make it public. There's nothing in there that's hopefully too sensitive. So the first thing is, how do you create a container image? And this is done using a Docker file. And so I showed you the first two lines of a Docker file. This says, what base image do I want to use? And when you say from Ubuntu 16.04, that means you get a full-on vanilla Ubuntu instance to start with that you can then start installing software on and running commands on. And every time you install a piece of software, it creates a separate layer in Docker that can add to the base image layer. So the Docker abstraction is a layered abstraction, and each command you run adds another layer that gets added to the original Docker container. Okay, that are modifying the original Docker container. Yeah. What kind of language? Yeah. It's sort of like a scripting language, I would say, because there are verbs. It's Docker's own. Yeah, I don't know. I don't know where the origins are from this particular. This is only for Docker. Yeah, yeah. This format is only for Docker images. And so these verbs are only for the Docker system to build container images as well. Okay, you can specify your name as a maintainer. And then you can run commands on that image layer. And every time you run a command, it's going to update that layer and then apply it to the base layer. Now, if multiple people have run that same command, what Docker does is it creates a hash of that command, the results of that command, so that you don't have to upload the same layer and have it replicated on Docker Hub. It will understand that this was a command that was run right after the base layer, and then you won't need to replicate the layer in Docker Hub. But that's just an implementation thing. What the abstraction I want you to get out of this is that you can just run commands to customize your Docker container after you specify the base. Then I want to do an apt update, and then I want to install Python pip because this container is going to run my Python Flask application. And so base Ubuntu I don't think has the pip package installed. So you have to update the package installer, and then so I'm running this on an operating system, and I have my code for my Python Flask app in a directory, in my current directory. And so this says copy the current directory into the container using the file path /app, and then I'm going to change into that working directory for the container. So this is a container operation, whereas this is copying files from your local file system into the container. And then I can run on that container, I can pip install the requirements in this current directory. So assuming that your application was stored in the current directory and it had a requirements.txt file there, then this will run inside of the container image a pip install to install all the packages into that container. Okay? And then the last two things are, how do you want the container to run after you start the container? So these are initialization commands on the container after you run it. And so you're encoding into the image, into the container image, that you're going to basically run Python on app.py as soon as the container starts. So that you don't have to actually log into the container and then run Python app.py. You are specifying to automatically run that when a container starts. So that is the most basic Docker file, and your Docker file for your homework number 4 is going to be very similar to this. Unless, of course, you want to win the prize, and you'll be doing all sorts of fancy optimizations to try and reduce your container size, because this is actually suboptimal from a space standpoint, but I'll let you dig into that only if you want with that. Okay, from that Docker file, you can then build a container image. And this is similar to make, the make command, if you remember CS410. So Docker build will go through that Docker file and will create the Docker image based on what's specified in that Docker file. One of the flags that you're going to use is the -t to give it a name. So every Docker container image needs a name, and every Docker container has a name. In this case, you are labeling the image that you're creating with that label. And so here is an example, Flask Hello World. So you can label this with a local name that is only that only appears on the machine you're building it on, or you can tag it with a Docker Hub image path. And this is similar to a GitHub path, where you're going to say the name of this Docker image is my Docker Hub username plus this. And then this will allow me, when I want to commit and push this container image, this will allow me to upload the container image to Docker Hub eventually. If you want to push your local container images to Docker Hub, then the command is to do Docker login. And you can point Docker login to either Docker Hub, to the Google Container Registry, to the AWS registry, to the Azure registry. The command itself takes flags to point to the provider you want it to. By default, it goes to Docker Hub, which is why there are no flags in this command. The Docker tag command allows you to associate a remote tag to a locally tagged one. So if I did a Docker build-t of Flask Hello World, but then I all of a sudden want to associate this local tag with a Docker Hub tag, then that's what the Docker tag instruction does. And then I can do a Docker push. And a Docker push takes that local image, the container image, and then pushes the contents to that account, the Docker Hub account. So this is very similar to what Git does. And I think this, basically having this abstraction mirror what you would do with Git is part of the reason this thing took off, the usability parts of this. Okay, if you want to download a container, it's Docker pull, just like a Git pull. And this will take that container and then get it locally onto your system. If you want to see all of the images stored locally, then it's just Docker images. And this is similar to doing an ls of /bin. Like you see all the binaries that are on your file in your file system. Docker images is basically like doing an ls on your containers that you have locally. And then if you want to remove images from your local store, because these things take up space, and if you don't have a lot of space on your operating system, then you can do a Docker remove image. So Docker RMI with the name of the container image. This is similar to removing a binary from /bin or doing an apt remove in your operating system to get rid of that image. Okay, so these are all image commands. So this is to basically manage container images. Eventually, you're going to want to run your container. And so the next set of commands I'm going to talk about are the container running commands. So Docker run will basically do a Docker pull, a Docker create, which creates the container, and then a Docker start, which will start the container up using whatever initialization commands it wants. So Docker run is what will both pull and start an image. So when I do a Docker run of this name, it's going to download the container if it doesn't exist, and then start it up. The flags that I'm going to show you are the -it flag, which runs the container interactively. So when you do a Docker run -it, it will actually give you a command prompt on the container after you run it. More often than not, you'll run it in detached mode, where you say, just run that container in the background, and then it'll bring up whatever services that it wants to. That's the -d command. You see this -p command. This will map a local host port to a container port. So the container has the full array of ports that it can listen on, but it's running on a host operating system, and it doesn't by default have its own IP address. It hasn't virtualized the network interface by default. And so if you want to map a host port to a guest port, that's what the -p flag is. And you'll be using the -p flag in one or two places in your lab. Okay. The Docker ps-a is similar to a ps command on Linux. This shows you all of the running containers. So the full-on containers are there. If you want to stop a running container, you just say Docker stop and then the name of the container. One of the things about the naming is when you do a Docker ps-a, you will see that the names for Docker containers are in two parts, separated by an underscore. And these are words that are easy to remember. And so when you stop a container, you can stop it using the name of using those names. And then Docker start is the opposite. If you stop the container and you want to restart it, this is Docker start. So the stop and the start is similar to stopping a process using Control-Z and then starting it up again using FG. I don't know if you've used this in Linux, but that's basically sending the stop signal to a process and then sending the continue signal to that process to have it start going again. So that's the equivalent. You can attach to the container if you want to and get an interactive shell. You can execute arbitrary commands on that container from the host using Docker exec, the name of the container, and the command that you want to run. Okay, this will come in handy if you want to look at the log file output of the container. Docker logs and the name of the container is where you would find all of the error messages. So when you're building your containers and you're finding nothing works, nothing comes up, Docker logs of that container will show you exactly where the thing errors out. So that's a useful command. Finally, if you have a running container image, if you've done a bunch of installation and you want to save all of that stuff into a new container image, then Docker commit will commit those changes into an image, and then that thing you can then push out up into Docker Hub after that. This is pretty inefficient in terms of space for the container, so it's not recommended necessarily, but that's a facility that exists. If you want to remove the container, then it's just Docker RM. And this is different than RMI. RMI is actually getting rid of the container image. Docker RM means killing that container, basically the runtime instance of the container. So this is like Control-C'ing your process to remove the container. Okay, there's this YouTube of a Minecraft UI to learn the commands that I thought was pretty funny. And I put that URL there if you're interested in watching the Minecraft way of managing Docker containers. There's one for Kubernetes also that I thought was pretty funny too. This is a picture of all the commands that I've just covered. So you have this registry up here. The Docker login will log you into this registry, and then pushes and pulls will take container images and bring them in locally. And so you have a local container store in your images. You do Docker images, Docker RMI, Docker tag, and this is based on the images. And then when you do a run, a run or a create, then you're actually creating the Docker container on your system. and then you can do the start and the stop and the exec and the attach, the RM and the PS. These commands all operate on containers that are running. And then from the container that's running, you can commit that to update the base image that they were started from. And then the last part of this is the Docker file that's used to do a Docker build to create a new image based on a Docker file. All right. So questions about Docker. So the best thing to learn Docker is to actually run a whole bunch of, to create your own Docker images and to use all of these commands. And that's what the labs are for. So we have 4 labs. The first one, you're going to clone the repository. And this is not container guestbook anymore. I think it's just container_lab is the directory. And this has all the files that you need to run this container lab. And so you can see in this Docker file for, in this directory, it's basically what I showed you before. So you're going to clone that, and you're going to cd into the container lab, and you're going to examine the application and the Docker file. This is very much like what you saw previously in the last class, except now there's a Docker file for you to build this app as a container, to upload it to Docker Hub, to download it back, to run it, and then connect up to it. So that's basically what you're doing with all these container labs. So you're going to build it, and there's multiple Docker files there. There's a Docker file Ubuntu, which uses Ubuntu 18.04 as a base image, and there's another Docker file there for Alpine, which is a minimal Linux distribution. You're going to build the Docker container on Ubuntu. You're going to call it Hello Ubuntu. You're going to go into Docker images to see that the image is there. You're going to run it in detached mode, and then by default, the application, I think, the application typically comes up on port 5000. When you do a Python of app.py, comes up on 5000. I want you to remap it to the host's port 8000 so that on the host, you can do a wget of localhost :8000, and that should hit your app that's running in the container. So that's the first step. And then I want you to do a Docker PS to see the name of the running container. I want you to do a stop on that container. I want you to show that it's no longer running, and I want you to start it up again. I want you to do a Docker exec of bin bash so you can get an interactive shell on that container. And then I want you to poke around. I want you to do an ls. I want you to do a ps. Navigate the container from within the container. Navigate to see what's there, to show all the file system and the processes that are running. And then exit out of that container. And then I want you to push this up to Docker Hub. So you do your Docker login based on homework number 1. You do a tag that associates Hello Ubuntu to your Docker Hub ID /Hello Ubuntu. I want you to push it. And then I want you to stop and remove the original container, and I want you to delete the original image. Both the original image and the Docker Hub ID /Hello Ubuntu. I want you to clear out all the images, because then I want you to do the Docker run from Docker Hub and to see it download and run the container that you've pushed up on Docker Hub. So that's the next step, this Docker run, and hopefully this works. Verify that this works. And then show the container image on Docker Hub, and then show the metadata. So MicroBadger is a site that if you give it a Docker Hub container name, it will go and inspect it to show you all the different layers that are there. So I want you to use some container tools to poke around and see what's actually in containers. Container lab number 2 is to do the exact same thing using the dockerfile.alpine, which is basically a minimal Linux distribution. And not everything is going to work the same way. So that's what I want you to do this lab. So you repeat all the steps using the Hello Alpine. Container lab number 3 is to bring up a VM on Google Cloud, to install Docker on that VM, and then to run the Hello Alpine container on this VM, mapping port 80 to your application port 5000. And in order to do this, you have to make sure when you create that VM that you allow HTTP traffic. So this allows you to then hit port 80, and then what Docker is going to do is route that port 80 request to the local 5000 port of the container that's running on that VM. And then I want you to show that it's basically the guestbook UI running on Google Cloud, on Compute Engine running a container is what I wanted you to see. Container lab number 4 is to run the container directly on a container operating system. So on Google Cloud, they have an operating system that all it's meant to do is run containers, and it will run containers natively. So the container, all of the ports on the container are mapped directly to the machine ports. So there isn't a underlying Ubuntu VM that's running it. You have this container OS that's all it does is run containers. And because the application listens on port 5000, in order for you to access a container that's using port 5000, because they're mapped directly to the physical port 5000, you're going to have to punch a hole in the firewall to allow port 5000 in order to get to the containers port. So part of this is to apply your VPC firewall rules, which you did, I think, in the networking part. You're basically going to do that same operation, but expose port 5000 to your VM. So this is what it looks like. You'll start by creating that firewall rule. You go into VPC network, create the firewall rule to allow port 5000, specify the tag HTTP 5000, and specify that you want that port TCP to be allowed, and then create a virtual machine to deploy your container on. So Container Lab 4, put it in the US West 1 region, give it a container name, hello Ubuntu, did I say Alpine or Ubuntu? Either one. And then when you select deploy a container image, it's going to select the container optimized operating system, and then you're going to add to this VM the network tag HTTP 5000. You'll bring up the VM, you'll see the external IP address, and then what I want you to do is SSH into that instance, and then make sure that your web app has come up. So go to that instance and do a wget of localhost :5000 to make sure that you get an index.html that basically has the guestbook HTML up. And that's when you know that it's successfully launched your container, is if you can get that. And then the next part is to make sure that you punched a hole through the firewall correctly. What I want you to do is go back into your web browser and then hit that VM using the port 5000 to pull the guestbook page. All right, so that's the last container lab. All right, questions? Yeah.
So, would you have to be doing labs on our virtual machines?
You can do them on the, They do not have on your Ubuntu VMs. Or you could actually do the labs. No, do it on your Ubuntu VMs is my recommendation. Any other questions? Yeah. As a tar pit for adversaries. So that's what Galwa is selling these things to enterprises, so that inevitably you're going to get compromised. Like everyone knows they're going to get compromised. Then it becomes a case of, can I either detect the adversary or slow the adversary down? Because the adversary is going to look to laterally move within your enterprise. And if you have this cyberchaff thing that's looking like thousands of hosts, and the adversary has to figure out whether or not those are real hosts that they should target or they're fake hosts, that actually slows them down. And if you have the cyberchaff node notify people that it's being scanned, because it has no legitimate use except for pretending to be vulnerable services, that's really powerful in an enterprise. And so it's a scale issue, because the enterprise doesn't want to put up thousands of servers to pretend to be tens of thousands of servers. It wants to put up one server that looks like 10,000 servers, and that's where you get the that's what that application is meant for. Yeah. Any other questions? Okay. 20 minutes. Sorry. I was trying to get you more time to do your container lab, but you should at least be able to do maybe one container lab. And then the other, they're pretty finite, the amount of time that it takes to run these container labs. All right.